Okay, so we don't have much time. I also have the tendency to go on too long. So I hope we can make it to 4 of these fallacies, and then we can see what will be left over for next week. I might actually talk a little more about specific neuroimaging things next week. But today is really not about neuroimaging very much. It's any kind of quantitative data analysis. So so here are the fallacies is a little strong. Some of these are not fallacies. Some of these are just points of clarification. I hope I can talk about these 4 today. Though these 2 are really dear to my heart because I've personally have heard them many, many times, and probably you might have heard them also, particularly, in our Columbia seminar, they often come up. Then I've seen them as a grant reviewer or paper reviewer. It's very hard to find them in print, these fallacies, but a kind of, they're entrenched enough that they're kind of analytic memes that people often take for granted. And I think they're very easily rectified, and that's why I want to mention them. Then these last 2, they're more standard, and they're not fallacies as much as points of clarification, in particular about probability base rate. I think this is really pertinent right now with COVID. Also, I find it very useful for any kind of diagnostic testing that you might undergo, in your own medical care. It's good to keep this in mind. And then the last thing, I think all of you are probably aware, for the last decade and a half, neuroimaging in particular has been sort of paying tribute to the replication crisis, or whether you call it overfitting or double dipping. It's a big point of concern. I think it's still worth talking about and illuminating with a few examples. So hopefully this is hopefully everybody will get something out of this talk and will be maybe even 10% entertaining, and these other things, the grade of things I'm not going to talk about today. We'll see if or whether we talk about them next time. So this is actually dear to my heart because for years, I myself have sat in a seminar and this came up all the time. And since then, I haven't seen it quite so much, but just a few weeks ago, I had it in the paper review where the fellow reviewer in the paper complained about the distribution of independent variable. And this was some associational analysis where people ran linear regression. The reviewer said, oh, these independent variables are not normally distributed. So therefore, there might be a problem with the linear regression formalism. And this is somewhat widespread. The textbook accounts, actually, this is a postdoc in our division recently brought this to my attention. If you go to this web link, there's also this, this is a respectable software company that's sort of making this fallacy on, this mistaken belief. So dependent or independent variables do not have to be normally distributed. That's the message. But why is that the case? So first of all, there are published references, particularly those 2 peer-reviewed. This one is one that a colleague of mine and I just submitted to bioRxiv because we had such a hard time getting this even reviewed. So we submitted this to, I think it was psychometrical methods. And the editor said, I cannot believe that somebody would make such an obvious fallacy. So I think this is a total red herring. What you're complaining about, I don't think you stated as a big problem in the field. I don't think it really is. So in other words, he didn't even see how somebody would commit this fallacy, right? But I want to at least convince you that, maybe you're all psychometrically astute and wouldn't make this fallacy. I have personally heard it quite a few times. So seen it on internet forums like ResearchGate, paper reviews. And what often happens is when variables are not normally distributed, people will advocate all kinds of variable transformations. There could be transcendental functions like arctan or logarithmic transform. The one, my personal favorite, is in a review quite a few years ago. I had to review a paper where people took the inverse of their independent variables just to make the variables more Gaussian distributed, because all of this is in vain. You don't need to do this. And I hope I can convince you of this. So first of all, I for years I always heard this in seminars, and I thought, why is that actually the case? Why do linear regression? Why does it necessitate the variance to be Gaussian, right? I myself, can't see why. Why would probing a linear mechanism the correctness of the inference? Why would that matter? How these variables are distributed. But okay, I'm not. There are many much more smart people than me. So first of all, I looked at formal textbooks, and there's one. This is like a classic in the behavioral sciences. There's also very nice econometrics. Longitudinal cross-sectional textbook by Woodbridge. And so you can look at other things too. So first of all, you never see you see that there's requirements for the residuals to be Gaussian in the case of small samples, right? In the case of large samples, even that isn't true. The only thing that you need is homoscedasticity or something, that the errors are not dependent on the value of the independent variables, right? So there's no mention of distributional assumptions on dependent or independent variables itself, just themselves. Only in the somewhat a special circumstance you have a low number of observations, then the errors need to be normally distributed. But if you have a lot of data, even that isn't true. They just need to be IID, or what's called identically and independently distributed. So the thing is, where does this mean come from? Did somebody once mistake the error, tenets for the variables? Hard to know, but somehow it's deeply entrenched, right? So let me first say something that you shouldn't confuse. There are various undesirable scenarios, right? The dependent variables, that they have measurement uncertainty, then the regression weights will be biased downwards. That's definitely, that's often the case, in all of science. If the independent variables have measurement uncertainty, sorry, I confused this. Dependent variables have measurement uncertainty, the estimates will be more variable, right? That's a given. Independent variables, if they have measurement uncertainty, and sometimes they do, sometimes they don't, right? If you have fixed task designs in psychology, for instance, there is no error, but if there's error, on the independent variables, then, you have a downward bias, right? And if you have non-normal distributions of independent or dependent variables, definitely the precision with which you get the estimates can be hampered. And I'm going to show you an example. If you have stupid designs that are very ill thought out, if you don't cover the whole range of possible variables, you might get, very imprecise estimates, but none of these scenarios invalidate the regression formalism, right? The inferential framework. I'm going to try to convince you of this. Yeah. So let's look at a thought experiment. This, for psychology, this is maybe the Drosophila of cognitive neuroscience, the famous Sternberg memory scanning experiment. Let's assume that we have the following data model. People have to remember some items, they study items, and for every item they study, when they get probed later, they have a slope of 40 milliseconds per item, and let's say a sort of intercept of reaction time of 300 milliseconds, right? Let's assume this is totally correct. I think it's pretty close to the truth. It doesn't matter what the slope value of the intercept really is. But let's imagine now we have this data model, and there's absolutely no measurement uncertainty at all. The error is zero. Right? That never happens in real experimental circumstances, but let's imagine that, right? So if you have, in this hypothetical scenario, where there's no uncertainty at all, we just need two values, and we have both intercept and slope. We can figure this out just by solving, the regression equation. We need two values, that's it, right? Any more values don't give us any more information, they follow just perfectly on a straight line. So these two measurements would suffice. And, there's the distribution doesn't matter at all because we have absolutely no uncertainty. Now, you could ask yourself, it's weird. So once you have measurement noise, then, the more data you have, the better, obviously. But now it becomes very strange. So at what size is the noise important enough that the distribution of the variables matter, right? It's a weird logical inconsistency. So you crank up the measurement uncertainty, and at some point, then all of a sudden, this dependence on the distribution would kick in. And now it would matter whether, the distribution values are clustered around the mean in a Gaussian fashion or not. And another thing is you can look at the formula for linear regression. I've given it here, right? And you can see, that the pins means pseudo inverse, but doesn't matter. But nowhere here, at least in the point estimates, does the distribution of variables come in, right? It doesn't matter how the variables are clustered in Y and X, right? The only thing you can see for this to work, you need homoscedasticity, meaning that the residuals are, independent of the independent variable. Otherwise, this formalism doesn't work well, but usually that's 99.5% of the time, that's not a problem. So yeah, so here I've said it already. It's kind of just, if you think about it away from math, it's weird. Why does probing a linear mechanism matter? How you cluster your probing values. Why should that matter? It would be very unsatisfactory, right? And the last one, this is a little tongue in cheek, is that you really think you're smarter than Johann Carl Friedrich Gauss, the inventor of ORS regression? He was a pretty smart guy. He stumped his math teacher in second grade, by being vastly superior to the teacher. So do you really think he would have not conceived or considered of these problems, right? So if the formalism is so easy to break, don't you think he would have figured it out too, right? So, okay, so now all of these are just arguments, they're not proofs yet. And, I know they're not the ultimate proof here, but I can show you at least with some simulations that this concern is misplaced. So let's take this data model, run 500 Monte Carlo simulations where we vary the noise level. I vary it widely. The item numbers are uniformly distributed from 1 to 8 items, right? So again, that's not a Gaussian distribution at all. It's uniform, right? We have 100 observations. Now we do linear regression and we get the parametric point estimates for the t-value and the p-value. And then each scenario, we do a permutation test with 100 iterations where we also get the empirical p-value. So how often do you find a slope parameter that lies in the tail of the null distribution? And you could ask, does the non-normal distribution of the item numbers lead to violations of any parametric statistics and PL inflation? And here's the scenario, and you can see, this is obviously where I made the noise so big that you don't have any effect anymore in the data, and you can see this clustering here. I should have done a logarithmic transform for you to see the bottom here better, but you can see there's no obvious p-value inflation, right? The scenario, if p-value inflation was there, then those p-values would all fall above the line. So the non-parametric real value would be much bigger than the actual parametric value. The parametric value would appear unduly small, right? So also now you can look again, just to make the point before, this is just to show you some of these simulations, the point estimates. Imagine we have a really idiotic design where most of the time we probe people just with 1 letter, and then one time we probe them with 8 letters. So this is really very collinear with the intercept term, right? Intercept term would be almost the same. You would never run a psychology experiment this way, right? But you can see even then the empirical slope is nicely distributed and you would get the right result, right? 40 milliseconds per item, right? But you see the variability of the estimate would be huge, right? Because this is a very poor design. Instead, if you take the uniform distribution, your precision gets much better, right? So this is just to make the point, you can use funky distributions of the independent variable that might hurt you because your precision is very poor, but the formalism isn't perturbed. It's not wrong, right? And that's exactly what I said here. And here's the last thing. This is just what I did this morning. sometimes people say, well, the independent variables, if they're non-normally distributed, that isn't so bad. But what about the dependent variable, right? And so I picked a null scenario here. We have a bimodal age regressor. This is real data. You can see, there's some young folks, there's some old people. And now I made a totally random uniform variable again. So the dependent variable is random, uniformly distributed, very non-Gaussian. These are null results, right? Null scenario. And you can see the parametric p level, if you just do a regression, you get a p of 0.1293. And here you can see the actual permutation estimate. 10, I think these are 10,000 permutation. You can see the t statistic is distributed as you would expect. It's centered on 0. And you see our two-tailed test also gives a value that's very close. So let me try. So I tried to convince you there is no problem if the variables are non-Gaussian. So now you could ask, is there never a case for variable transformations? No, that there might be a case for variable transformation, and there are valid reasons. Just what I'm trying to convince you of, not the distributional hygiene. So you shouldn't start transforming variables only because they look strange in the distribution. There might be good reasons for transforming. You might know the right data model, right? If you know, in the Sternberg example that I gave, I could log transform everything, that would still work, but it would be the wrong model because we know there's a linear dependence on reaction time, right? So if we know the a priori model, then that information should be used, right? Then another thing is interpretability. That's a prime example for logistic regression, right? I can predict a logit function of a class probability ratio. That's much easier to understand than predicting an arbitrary class label, right? So in this case, I have good reason to transform, right? The only thing is, again, distributional hygiene shouldn't be your concern. So the conclusion is, as formal textbooks indicate, by omission really, the distribution of independent or dependent variables is irrelevant for linear regression. Distributional assumptions to motivate variable transformations are also inappropriate. It's interesting, sometimes this becomes so entrenched because of the sociology of the field that people acknowledge, oh yeah, we don't need to transform, but it's become the tradition of our field or the convention. That's what everybody does. I can't break with that for fear of penalties, right? And the last one here, this is my real suspicion. Everybody is busy and slightly lazy, and often paper reviewers will look for something to say, and this is something that you can very easily lodge, this complaint about distribution, right? You don't need to think about matters of design or science so much. The independent variable looks strange. Let me bring that up. So I have to say, I have something to say. Okay. So, and I think that's the end here. If there's any questions now, would be a time.
Yeah. So
them up.
Are there any questions?
Okay. I have a small question, if I'm allowed.
Yes.
Sure, absolutely. I'll try my best.
It's purely theoretical one. I personally never heard of this fallacy because never the Gaussian distribution of the data never was a requirement. I never heard this requirement for linear or any other fit. But after your presentation, I thought if your data is distributed in non-symmetrical distribution or a distribution which change shape with mu, for example, log normal or Poisson. In this case, your residual will be dependent of the value. Will be will this be breaking your reasoning? And if you have some Poisson, you cannot do any linear fit, or linear fitting will be unreliable.
Yeah. So I can only say if so. The one thing that needs to be ironclad is the homoscedasticity. So your residuals cannot be dependent on the independent variables. If that is, now I'm not sure whether that's the case for Poisson distributions or any others, but if that is the case, then you have a problem, right? So that I agree, but that you can also empirically check, right? You can inspect your residuals and see whether there's any dependence, right? But I would be that's by the way also the message. Don't take any authority or don't believe in distributions that somebody declares. Just check it for yourself. Now there are other statistical tests that do require Gaussianity and certain assumptions. Linear regression does not, or you only need it for the errors, right? The errors in small samples. They need to be IID and Gaussian. If they're large samples, they just need to be IID. So.
Okay.
I mean, if you haven't heard of this, then yeah, that's in a way good. I've heard of this. Let's say I hear about this maybe 4 times a year at least. This kind of thing comes up. So. Okay, should I move on, Ariana?
Are there other questions? Because otherwise, I had questions about the. So you show that the distribution of the data can affect the precision of the estimate, right? So even if it is okay, so it still makes sense to use linear regression. But when would you say that it is useless to use it because the estimates are so bad, so imprecise that they're not providing any meaningful information actually, because they are just too imprecise environment? Is there a cutoff? Is there a test?
Yeah, no, I don't think I can give any kind of that, because that's all a matter of good experimental design, right? So if you say if you did a shoddy job, for instance, coming up with an fMRI experiment where your precision is so poor that you cannot, get at the contrast you're interested in, you should be able to check that yourself with the formalism right before. And I can't give you a blanket, absolute hard-coded value for that. But say you have a very low, a very noisy signal, and you design an experiment with very few trials, then you should be able to figure out beforehand that, oh, this is kind of pointless. I'm not going to get my power, for differentiating between the control condition, my experimental challenge will be very, very low. So, but I can't, as an analyst, it's funny, people always want the analyst to tell them, want to give them the sort of revelatory truth, and I can't do that. Sorry.
So it was an attempt to pursue this tradition. Okay. So if someone has questions, maybe you can type them in the chat, and I think we can go on because it's already 3:30. So
yeah. I'm going even slower than I wanted to, but that's okay. We don't have to rush. So so the next one I really love because it's very easy. It's very easy to explain, and this is another one that I have heard many. You don't hear it in print very much, but I've sort of implicitly I've heard it in a lot of reasoning where people are reasoning about the behavior of 2 variables to one another and how they behave to a 3rd variable. Often people will make sort of spoken inferences. But so this just for good, so transitivity of correlations, right? That's the fallacy. And so let me give you this. I can't do this. This is with students, it's much easier to do because you see a seminar room and you can ask people. Also, not to put you on the spot, but if A correlates with B and B correlates with C, what can be said about the relationship between A and C? So that would be normally now the question, and I would ask, anybody has an answer? Hard to do over Zoom, but maybe also what's coming. The answer is nothing whatsoever, right? Because correlation doesn't behave like a normal norm function, right? There is no transitivity there. And I'm going to show you that with the counterexample very easily, but this comes from a real grant review. Like a while ago, a colleague of mine, she wants to study, her thing is studying diet and the effect of diet on neural inflammation and then the effect on cognition. So she it's known that neural inflammation is associated with cognition, right? There's a reasonable body of literature. So she wanted to study whether diet will affect cognition via the mediating mechanism of neural inflammation. The reviewer, one of the reviewers, wrote back and said, this study is superfluous, right? You don't need to do it. It has been shown that diet is associated with inflammation. So A correlates with B, right? Inflammation is associated with cognition. B correlates with C. So therefore, diet is necessarily associated with cognition. A correlates with C. Case closed. Why are you proposing this study? We could save a lot of money and time because we already know that diet will affect cognition, right? So that's the fallacy directly in the real world, where and so if you listen closely, often people will, so sometimes you will have relationships A with B, B with C, and then people will make some kind of inference. This also holds about being independent of, right? Not only about the correlation between, but also if a lack of correlation is there, then people will assume that B and A are perfect surrogates in their relation to C. That will often come up, or at least in my world, similar discussions. And we have this fallacy is great because the mathematical demonstration is so easy that you just can come up with one counterexample, right? That's very easily appreciable by everybody. Imagine, now let's stick with the diet example. Imagine we have a bad junk food dietary variable, right? Doesn't matter. I made this up, but imagine there's a variable B that's, you can quantify to how junky your diet is, or there's this great acronym SAD, the standard American diet, SAD. So how sad is your diet? The higher the value, the sadder that your diet is. Let's imagine a cognition variable, total cognition, maybe, episodic memory, reasoning, speed, and vocab all in one thing, some kind of crystallized intelligence. And now let's imagine an inflammation variable. We make this up again. This is all, hypothetical data. We just take D minus C, right? We subtract C from the others. Let's assume these are dimensionless. We subtract them from one another. This inflammation variable will have a residual correlation with both D and C, right? But D and C themselves are uncorrelated because I generated them, I sampled them from normal distributions randomly, right? It doesn't matter what distribution they are really. I just sampled them randomly, made them up, right? And then this mediator I constructed using both of them. And now you can actually plot these pairwise relationships. You see, it's a little faint to see. I hope you can see it on the screen. We plot diet against inflammation. That's, we have a nice positive correlation. Our sad diet sort of leads to inflammation. We also have inflammation being related to cognition. Worse inflammation will give you worse cognition, right? So we have A correlates with B, B correlates with C, but per construction, A is uncorrelated with C. You could see here, right? It looks like bird shots. There's no relationship there at all, right? So this is the refutation of this reviewer who was so unsophisticated. Just because you have empirical correlations between two variables here, it doesn't mean that anything follows about the third unconsidered correlation. And this is also general caution when interventions are advocated only on account of empirical correlations with surrogate endpoints or biomarkers, right? Imagine now you think, I'm absolutely convinced, inflammation is a perfect surrogate for cognition. Therefore, I just need to be able to, keep inflammation low, and I already have definitely affected my cognition. That's not the case. You need to really verify mechanistically or with something called mediation analysis that really is the case, right? So that is the fallacy already, and it's actually very easily refuted just with this counterexample. And maybe hopefully there are not too many questions about that. If somebody, so you should just, your ears should perk up if you hear, you know, for instance, this is one thing that I always hear in our seminar, or, you know, age is correlated with a certain, you know, age is correlated with cognition, you know, we found, you know, that a particular, you know, brain activation or say even a brain structural signature is correlated with cognition or with age. Therefore, we also assume it to be correlated to the other variable. And you have to say, no, that doesn't necessarily follow, right? You need to verify that empirically, right? The linear substrate of a variable isn't necessarily related to another variable that the original variable is related to. Right? That's a very convoluted way of saying. Just because A correlates with B and B correlates with C, it doesn't mean that A automatically correlates with C.
But if you have a case like this, so A correlates with B and B correlates with C, are there some, let's say, the relationship between A and C, are there some R values that are more likely than others?
Yes, yeah. No, that will be the case. The R value probably, and I can only that you would have to simulate, or no correlations. The higher the correlations, that probably the more likely it is you find also relationship. That might be the case. Yeah. But the beauty is, I mean, if you have, I mean, you can verify empirical correlations yourself, right? That's the beauty. It's just when people say, oh, you shouldn't run this experiment or gain this data, you know, in the same people, you can assume already that A correlates with C, then your ears should perk up. Yeah. Okay, should we move on? And
unless there are other questions. Okay.
Just could I maybe just jump in?
Sure, absolutely.
So I mean, in this case, you would surely just simply apply a mediation analysis to see if there is a relationship between the third variable and the other two.
Right.
No?
Right. Surely, yeah.
Okay.
You would do that, but the example, you know, the grant example, that's exactly what the grant wanted to do, right? The reviewer already sort of obviated the need for getting the data in the first place by engaging in this fallacy. But yeah, no, you're absolutely right. Ideally, you can plot the correlation A with C yourself, and then you should also go and do Preacher-Hayes mediation analysis. That would be my thing to really show the
Okay, great. I was just checking I was on the right lines.
Yeah. No. All of this is common sense stuff. This is not particularly, you know, you don't need, you know, access to special, you know, higher power. Right? So, okay.
And I suppose that, Chris, I don't know if you agree, but I mean, if in your study you measure A, B, and C, it's kind of obvious to run a mediation analysis to verify. But I think this fallacy maybe comes up more often when someone does a study on A and B. Then there is evidence in the literature for relationship between B and C, and then we infer that A and C are related, but it's, of course, it's speculation. But sometimes maybe we tend to do it.
Yes. No, they're absolutely true. And also, I mean, correlation, even a t-test is a kind of correlation. So if you, even as, you know, if you have two different studies where A is bigger than C and B is bigger than C, right, you would be very tempted to say A is bigger than C, right, even for mean contrast. But even that is problematic, right? So you should ideally have all this information in one study or one analysis and then check yourself. Yes. Okay, so let me, you know, we're running out of time so fast that I might just cut down the biomarker. This I think most people might know anyway. So maybe let me just go directly to because this is always, I think you can never talk about this too much, and it's always interesting, and there are always some facets that even I, you know, that I always learn again, and arguably this is more important for our science than the biomarker base rate difference. If there's, we could see whether people will still want to talk about the other thing. I could do this next time, or we could cut it out entirely. So anti-Occam's razor and overfitting or double dipping in neuroscience, and obviously the other, very data rich and theory poor disciplines, let me call this, when you have lots of data available, but not a very good knowledge base of a priori models. And arguably this applies to all of them. And, in particular in the life sciences, I think since 2009, we are more aware of these errors, and the NIH has spent a lot of, and I'm sure in Europe similarly, NIH has spent a lot of time addressing this, also in grant reviews. And so, first of all, there's some good. This is also fun, to read about in other contracts. There are various sources. These are all the sources I thought were pretty at least enjoyable, and good fun to read. There's a really nice wildlife ecology website. It's now quite old, but it's called The Insignificance of Statistical Significance Testing. A little bit tongue-in-cheek, the title. Then there's a Two Economists account, The Cult of Statistical Significance. And these criticize a little bit more sort of frequentist inferential frameworks in general. Then papers by E.J. Wagenmark are always good. This one I thought was a very nice one that made some of this point. And then Nicholas Nassim Taleb, who I think these books are, one of them is interesting to read. Maybe some of you have read some of them. They kind of make the same point over and over, just in interesting ways. And then he pokes fun at Wall Street traders who are sort of are semi-quantitatively literate. And so he becomes very sort of repetitive, but The Fool by Randomness, at least I found when I read it first quite a few years ago now, I found it an enjoyable account, and I'll give some real world examples. But so it's sort of an interesting cultural history by now, because this is now time is racing, particularly for people like me, middle-aged guys. Time is racing even faster. But this seems it was like yesterday. But in 2009, there was this start of the double dipping debate, and there were these two very influential papers by Wool and Paschler, and I think this was Kriegescourt and et al. And both of them criticize analytical practices and cognitive and basic neuroimaging, and that kind of caused major controversy. Particularly Wool and Paschler really singled out social cognitive neuroscience publication. They actually listed the papers and criticized, really pinpointed the errors people had made, which obviously got some people really riled up. I also think it's a little bit unfair that they did this, because it somehow seemed to suggest that social cognitive neuroscience was the only field afflicted by these problems, when it's pretty clear it's the life sciences, even medicine across the board, right? And so replication crises are found in many science fields. Psychology has to be reasonably open about it. There's also the replication project, and there are many authors that have chimed in. Some of them I've mentioned already before. They've given enjoyable accounts, right? So what's the reason for double dipping or overfitting, or coming up with results that won't replicate? And neuroimaging in particular, my discipline, is extremely complex, right? It has a lot of pre-processing that has to be done, selective stages. These stages make up whole careers of expertise. There are people who just focus on motion correction, for instance, or slice timing correction. Then the difficulty of exact repetition of analytic recipes, and lack of provenance, software updates, and so on. The NIH, and I'm sure in Europe, similarly in your funding agencies, a lot of effort has been spent on that, just to make sure that exact repeatability is now more possible than ever, right? You can download software, data sets, my life, I feel, has become much harder because of having to deposit data sets and methods always with most papers. But then I think it's also systemic and cultural, that data exploration used to be sort of frowned upon. Exploration is quite important, and it was seen as a pejorative thing. And very often it's disguised as rigorous confirmation of a prior hypothesis, even if that isn't true. And that's probably the reason why so many things don't hold up. It's a penchant of the field for spectacular findings, and you want things to be rigorous, right? So there's pressure for publication, career success. And then there's also the file drawer problem. That's another one where null results are not really published, although they should be, and so all of these feed into it. It's probably less often that there's widespread and committed fraud that's committed where people are really dishonest. It's probably these little nudges that push you one way, right? And it's very easy to fall in love with your own data and your own idea, right? Okay, so this is a great example. I love this example because it's in a way so simple, yet it's really profound. And again, I didn't come up with this. I saw this, I think, in a paper by Wool and Canvisher. But imagine you have 4 dice and you throw them and you get the combination 3, 4, 2, 6. And the probability of obtaining this particular dice throw in that order, you can calculate as 1 over 6 to the 4th power, so that's 0.07%. And you tell yourself, wow, that's amazing. It's amazing. Wow, what's the probability of getting such a throw combination? And this seems kind of strange, and Canvisher and Wool articulated this too. Imagine you can do this every time, right? And imagine you have a friend, every time you throw the dice, they go, oh, wow, it's amazing. This particular combination comes with such low probability. So what's wrong with this, right? Isn't the formula here correct, right? And, I myself I was stumbling about this originally. What is amazing, the silliness of this above example, as soon as you ask, what is this probability computed in reference to, right? The formula is a total red herring. It doesn't matter because somebody needs to announce this particular, combination beforehand, before you throw the dice. Only then does the formula come into play, right? If I make no prior prediction, this is totally irrelevant, right? So, one way to think about it is just imagine you play the lottery and would you be very surprised by the non-winning combination of numbers? In other words, your number doesn't win, somebody else's number wins. Would you then make the same? Would you show the same astonishment, right? So, in other words, this formula only makes sense if there's an a priori prediction, right? So, in other words, a posteriori, after the fact, computing things is really useless and irrelevant, right? And that's the heart of the double dipping problem. What I've shown you here in this very stark example, a much more diluted form, is happening when you do double dipping. Often you're not aware, right? Often you're not aware there's something going on and you think you're engaging in the right formula, but what you're doing really is not appropriate anymore. And here's another example, right? In this case, it's pretty clear. Imagine you have the stock prediction scan. You take a particular stock or the Dow Jones or some index, and you predict 10 weeks out, and you have an up-down prediction. Okay. And you can generate all the sequences of up and downs. You have 1,021 possible binary sequences, right? And you mail these to 1,024 mail recipients randomly, right? You focus on one stock. And after 10 weeks, you offer the recipients to sign up permanently for your annual newsletter, for $1,000. You say, I offer you to predict, if you like my predictions, then sign up for this newsletter. And just by peer, this is kind of a Nassim Taleb-like demonstration. Just by, if you plot the number of correct weeks here, right? That's a nice Bernoulli, a nice binomial distribution, right? So just by pure luck, dumb luck, one person will have received the correct prediction for all 10 weeks. The 10 people will get 9 weeks of correct predictions, 45 that will have 8 weeks of correct predictions, and 120 that will have 7 weeks of correct predictions. And let's take all the other ones. Let's discard them. We're not going to bother with them, but we did good bookkeeping. We know who these people are, and we offer all of them the special subscription rate, right? So they were part, in a way, of a double dipping experiment because I just brutally enumerated all possible stock behaviors, right? I had absolutely no knowledge about the stock behavior at all, right? I generated all possible results, and then afterwards just picked the ones that were correct in order to offer this, so lucky winners, could sign up for this prediction, but I didn't predict anything. There was no knowledge at all, right? It's just dumb luck, right? So that's a form of double dipping. Then here's a more subtle one, and this can also show you, this is again mock data that wasn't really, this wasn't really measured, but I made it up. Imagine you take CSF tau levels in the body, and you want to associate it with body weight. Yeah, this is totally hypothetical, no. Let's imagine you're funding for 30 human participants, but you do 15 and then you go, lumbar punctures are really painful and costly. Let me start peeking at the data. Once I have 15, let me, check whether there's correlation between the CSF tau levels and the body weight, right? And so you do this, you start peeking at the data, right? Because you want to, you're going to stop once you get a correct, significant prediction, you will stop. So imagine you have a significant correlation that you find after 21 subjects, and it's significant just at 0.03 or 0.04. You conclude the study, you write up the results. You don't mention the peaking process, right? And in the back of your mind, that that's not really ideal. You heard somewhere that, this only holds my parametric formula, the calculus only holds if I have a pre-planned study. I can't really iteratively peak like that, but how bad is it really, right? And now the problem comes in that there's no a priori, your decision rule to stop. I don't even know how to do the statistical inference, right? So, but what you can do something called a Monte Carlo simulation, where you generate null data and then you peak many times. And you can, again, you can take the nominal p-value that you get at the end in the last possible test, right? And now the number of how many tests I run, I know I run at least 15, but up to 30, right? I don't keep track of, how many tests I ran, but I stop once I get a significant result. And you can see, you can compare the actual nominal, the actual empirical p-value, from the permutation test. You can compare this with the nominal value. You can see there's p-value inflation here, right? If I think that my p-value has a particular nominal value, the real empirical value is higher, because even if you have null data, if you start peaking, then sometimes some part of the time you get a significant result, right? So it's surprising the inflation isn't quite as bad as I thought, but it's definitely not significant anymore if you apply the 0.05 value. So, but also, is that the right thing to? It's hard to really incorporate peaking and stopping into a formal calculus. But here, you have an example. This is something that might happen. You might want to look at your data. If you do, though, do not go the whole 30 subjects and then report the last people. That's the right thing to do, right? And then here, here's a standard overfitting example that maybe most of you have seen. I'm not going to discuss this very much, right? If you overfit and you take a polynomial that's much more complex than the model, you might get very large residuals in the remainder. No, let's rush through that so that we don't need this. The last thing is, yeah, this is maybe more important. Overfitting can also be done algorithmically. So in other words, even if you don't do, p-levels or one-shot regressions, imagine you do variable selection. Here, imagine I have 353 individuals. This is real data. I have 68 free surface regions. We have surface, surface regions with cortical thickness, and have a measure that's total cognition. And imagine now I have, I pick out of these 68, I want to know which ones are the best 10 to pick to predict cognition. So then just by brute force, I do 10,000 times, I pick, random sets of 10 cortical thickness regions, right? So now I'm doing something called variable selection dredging, right? So I do this many, many times, and I can split my sample into a training sample, 100 people, that's where I do the dredging, right? Actually, in this case, I think I'm doing it everywhere. So in my training sample, I can observe how well these 10 regions fit the cognition. Then I can check in sample 2, right? That's a kind of replication sample. And then I have a third sample. That's my second replication sample, right? And you can see, if I show the results here there's the logarithmic p-level in my training sample, right? And here is the predicted residual sum of squares in sample 2. And then sample 3 I can't show because I don't have a three-dimensional plot here. But you can see you want this value to be high, right? We want the p-level to be low, meaning the logarithmic p-level should be high, right? And here is my predictive residual sum of squares, right? This value should ideally be low, in the replication sample. We want the residuals to be small. And you can see here that whatever gives you good residuals doesn't have the best model fit in the training sample, right? So if you were to take the best fit in the training sample, which would be somewhere here, right? That's these 2 points here would give you, this is the best fitting model in the training sample. You would not get something that works very well in the held out data, right? So this also shows you can algorithmically do commit double dipping or overfitting by running many analyses and picking the best variable subset. That's one example of algorithmic overfitting. Would be much better if you leave one out cross validation or some other things. Okay.
Chris, sorry, yeah. We need to close in a couple of minutes.
Okay. So that's so here are some examples. Don't peek at the data. This is very easy to to sort of fool yourself, see where the data leads you. Don't do things iteratively. It's always good, write down your analytic recipe beforehand, and then also think about what would contribute good replication, right? Then data exploration, as I said, it's a good and necessary thing, but be clear when you are exploring and maybe set aside some portion of the data where you can replicate or validate, right? And we're not going to talk about publication bias. That's a kind of overfitting, or at least biased reporting, where you sort of leave out the null results. You could look at that as one kind of overfitting, or at least you're selectively only reporting data, and that gives you the wrong results for meta-analysis. Okay, so I think we can finish here, and sorry it was a little rushed, but hopefully you got some of the flavor.